Hello from a sunny afternoon in Lausanne, Switzerland, and welcome to the third installment of the CCAM Mixed Generations series. So my name is Sara Bonella. I am here to play host for you this afternoon. The topic of this third session of our Mixed Gen series is quantum Monte Carlo simulations. And we have three interesting speakers lined up. David Sepperly, who I hope will turn on his camera and join us on video now, followed by Juha and Michele, who will...
I can't actually turn it on. You've blocked me.
That's very bad. Maybe Guy can do something to fix that problem or bug it. Okay, let me briefly... Here you are. Good. So the goal of this new CCAM initiative is to create an opportunity for the younger members of our community to share the work and learn from more experienced scientists. We've had two sessions so far. The first one on activated events, the first one on, activated events with Chris Del Lago as a main speaker, followed by one on active matter with Julia Yeomans, Quantum Monte Carlo, David Sepperly today, and we have three more appointments lined up for April, May, and June with Claudia Draxel, data-driven science, Michele Ceriotti, machine learning, and Alessandro Laio, again on rare and activated events. The format of the series, we start with one talk by an experienced speaker. This is meant to be an introductory but advanced talk on the topic of the day, followed by two shorter seminars by youngish members of the community who share their work with us. I have a couple of pieces of information to share with you before we can go to the actual session. And here we are. I just wanted to remind you all that this session is being recorded. The reason why we're doing this is because we are creating an archive of this lecture together with all the lectures of the series. And these will be available both on the CCAM main website and on the CCAM YouTube channel. Keep an eye out on Twitter to know when they go live. The structure, as I said, we start with the first talk, and this is a long talk. So we are going to enable you guys to ask questions throughout the talk. To do that, please use the Q&A feature of the Zoom webinars. For this questions that you ask during the talk, I would ask you to type them down, and then I will relate them to the speakers so as not to interrupt the flow too much. Then when the talk finishes, David will also take more questions from the audience. In this case, we would like to have them from your voice, so you will be allowed to speak in the webinar format. So just type in the Q&A that you want to ask a question, and then when your turn comes, you will be invited to unmute and you will be able to ask your question straight away. So if there is a back and forth between you and David, this is going to be possible. For the second and third talk, these are shorter, and so we are not going to enable questions during the talk, but there'll be plenty of opportunities for you to ask the questions at the end of the talks. And again, here, just let me know that you want to ask the question, and when your turn comes, you will be just asked to unmute and then ask the question live. The rules of the game are that you are not able to activate your video for the whole duration of the Zoom session. I'm sorry. So this is true also when you ask the question. We will hear your voice, but not see your face. And that the chat feature of the webinar has been disabled for the entire session. So I think this is all I had to tell you in preparation of our afternoon of science. So without further ado, I would like to give the floor to David Sepperly, who will present to us an introduction to quantum Monte Carlo. David, you have the floor.
Okay, thank you. Can you hear me?
Very well.
Okay. I guess you can see this okay. In this lecture, I'm going to tell you about some features of quantum Monte Carlo, some general methods. I can't go too deeply into any of these things in the format. What I'm going to talk about are the simplest generalizations of the classical methods that we use to simulate systems, that is molecular dynamics in Monte Carlo. There are many types of quantum Monte Carlo, I should say, and I'm not going to cover them. The most common ones work in a discrete basis. For example, a lattice model like a Hubbard model or a Heisenberg model, or lattice gauge theory that's used for in high energy physics. There are also intermediate methods, which I call second quantized methods. For example, full CI quantum Monte Carlo, which is using chemistry, or auxiliary field quantum Monte Carlo. These work in a basis of occupation number in basis. And of course, they can be used to reach the continuum limit if the basis becomes complete, but they're not usually done that way. So I'm going to talk about only methods that are formulated in continuum space, and they're most useful for strongly correlated systems. If your system is well described by Hartree-Fock or density functional theory, you would not necessarily use these methods. But I'm not going to discuss applications very much. But my one example is liquid helium, which is a strongly correlated system, as I'll describe. And so the three types of methods that I'll talk about are, first, the ones that so-called finite or non-zero temperature, which is path integral Monte Carlo. That's the method that has the closest connection with classical molecular dynamics or Monte Carlo. And the second two methods are single state methods, zero temperature methods, which are variational and diffusion Monte Carlo. Diffusion Monte Carlo is an example of projector Monte Carlo. Now, there's another method that Michela, who's going to talk after me, a couple of electron ion Monte Carlo, actually combines these two things. So I'm going to let him describe that. Now, just to give you, so then the natural domain for these methods are strongly correlated systems that are typically disordered, and liquid helium would be an example. Or we talk about, Michele will talk about liquid hydrogen and solid hydrogen. So, you have a lot of disorder. And so it's not like a problem where you're trying to calculate the energy of a perfect solid, but of a disordered solid. And with these methods, you can treat many particles, not as many as classically because they're quantum mechanical, but you can treat for bosonic systems. There's a big difference within quantum Monte Carlo between bosonic and fermion systems. For bosonic systems, you can treat 100,000 particles. You may not need to do that, but it's, we have done that. But when you treat fermion systems, because of the anti-symmetry requirements, 1,000 particles would be a typical upper limit. Although these numbers are not set in stone. I mean, obviously you can do more. And if you had faster computer, more parallel computers, you could do more. Okay. Now, to give an example of a quantum system, which is the first system that we worked on, is helium. Now, in general, helium is, it's the prototypical quantum system. That is, it's an example of a system that you can't solve very well with other methods. And there was controversy for many years about whether Bose-Einstein condensation was responsible for its superfluid properties. Let me describe the physics of helium a little bit more. A helium atom is really like an elementary particle because when you're at the first electronic excitation is 230,000 degrees Kelvin. So if you're at low temperature, that is 4 degrees Kelvin, there's no possibility of having electronic excitation unless you induce it experimentally. And the interatomic potential between helium atoms is known more accurately than any other atom because these excitations have so much higher energy. And on the right over here, we show that the two-body potential, that is, of course, there is a little bit of a three-body potential, but the solid line is like an experimental or something from quantum chemistry, and the dotted line is the Lennard-Jones potential. What it's characterized by is a very strong repulsion at distances less than 2.5 angstroms, and a very weak attraction otherwise, this van der Waals interaction. And because helium has such a light mass, it doesn't easily form a solid. Now, the other things that are nice about helium is there are two isotopes, helium-3 and helium-4. Helium-3 is a fermion because it has an odd number of fermions, and helium-4 is a boson. Okay, so you can study the effect of statistics. And there have been a lot of experiments, and they're very clean experiments, much cleaner, say, than cold atom experiments because it's actually stable. You know, you could send helium up on the space station and do an experiment there, or you can, it's routinely used in laboratories. Okay, now here's the phase diagram of the bosonic system, helium-4. And what I was saying before is because the interaction is so weak, it's the only element that is liquid down to 0 temperature. In particular, below 2 degrees Kelvin, this is pressure and temperature here, below 2 degrees Kelvin, it goes from a normal state into a superfluid state. And there are a lot of questions about what this superfluid state was. I won't describe it in too much detail, but one of the goals of computer simulation that we actually did in the 80s was to start with the known Hamiltonian, namely, you have a potential that I showed you before. R, by the way, capital R refers to all the coordinates of the particle, all the n atoms. And so you have a potential energy, which is pretty well known from other things, quantum chemistry or from experiment. And you have a non-relativistic kinetic energy. I often use the symbol lambda for h bar over m. Because the mass is low and lambda is large, there's a competition between potential and kinetic energy, which you do not get so much in other elements. Okay, now the basic framework in order to understand it was provided by Feynman in 1953 in terms of imaginary time path integrals, which I'm going to talk about. And of course, in 1953, there weren't the computers or the algorithms to do these things very well. But now, if we were going to do simulations of helium, what do we want to do? Now, if you're doing a classical Monte Carlo, you do an integral like this, right? This is the partition function. The average potential energy is given by the integral of the coordinates, and you have the Boltzmann factor here, and you have your potential energy, and this is the partition function, right? In beta is 1 over kT as usual. Now, quantum mechanically, you want to do the same kind of thing, except what replaces the Boltzmann distribution is the diagonal part of the density matrix, which I'm going to describe in a minute. Okay, so, but you basically have to do this many-dimensional integral. So of course, you're going to have to do some kind of a simulation because there's no reason that the quantum mechanical average is easier than the classical one. But in addition, you have to have a method to generate the density matrix, right? I mean, we know the mathematical expression, but we don't have an explicit form like that. And that's what path integrals do for you. Now, what is this density matrix? Well, it's really easy to describe. Suppose mathematically to describe. Now, this is the Hamiltonian. If we have a complete set of exact eigenfunctions, phi alpha, okay, the density matrix is basically you put the particles in the state alpha according to e to the minus beta e alpha, right? That's the probability of being in the state alpha. And then phi alpha squared is the probability of having the configuration R in that state. So that's basically the probability of being at position R. Now, or you can write it in operator notation as e to the minus beta h. Now, the important mathematical fact is that for the non-relativistic Hamiltonian, this density matrix is non-negative, okay? And the second fact is that you can factorize it like this. That is, if you have the product of two exponentials, you also get an exponential, right? But beta here is 1 over kt. So by factorizing it like this, you're going to higher temperatures, right? You can write this in configuration space. This is just a different notation as this convolution theorem, right? This is an exact property. Now, Feynman saw that this gave you a way to write down an explicit expression. Trotter wrote down the mathematical theorem or formula, which is the following. Namely, this is the density matrix again, but now we've recognized that it's a sum, the Hamiltonian is the sum of kinetic plus potential. And you can let these density matrix commute with each other and factorize it into lots of little pieces. And this is the Trotter's formula, namely the density matrix is written as the limit as you make lots of little products. Tau is like the time step in molecular dynamics. You're doing the same thing when you do Verlet's algorithm in molecular dynamics. You're breaking the trajectory into lots of little time steps. Or you can do the same in quantum mechanics, right? So that the density matrix is the limit as your time step goes to 0. M is the number of steps, and tau is beta over m. And you can have the density matrix for the kinetic energy and for the potential energy independent of each other. And so it's like in molecular dynamics, you propagate forward with a force, and then you reevaluate the force and you propagate another step. We do the same thing. Now we can write down explicit expressions for these kinetic and potential operators now, because this is for free particles essentially. And the kinetic one is the Gaussian and the potential one is just the potential energy, okay? And the reason the Trotter's formula works is that the errors are like the commutator, the potential and kinetic energy times the time step squared. So as tau goes to 0, the errors go to 0, okay? So you put this all together and you find that what we want to sample in quantum systems is a path integral. Namely, we can write this as the partition function is the integral over all paths. And then we have this, what we call the action. And the action we just evaluated on the previous graph is basically we have a kinetic part and we have a potential part. And so this is like a polymer, basically, as I'll show you in the next one. And the second thing is here, we want to calculate the partition function. That means we want paths that close on themselves or ring polymers. And so here's the picture that I hope is somewhat familiar to you. Here are 6 helium atoms in this box right here in 2 dimensions. And each atom turns into a path, which is like a little rubber band, right? The start of the path is this black dot. So we have 6 atoms, we have 6 paths. The probability of the path is given by 2 terms, the potential part and the kinetic part. The kinetic part is the stretchiness of the rubber band, right? And the potential part, it interacts between various elements of the rubber band. So the dots interact. So because helium is like a Lennard-Jones potential, the dots cannot get close to get other because they're excluded, and they attract when they're a little bit further apart, right? It's the same with every point on the path. Although we labeled one point on the path with the dots, all the points on the path are equivalent to each other. We have a symmetry. As you go down to lower temperature, the paths get more and more spread out. And this will lead to the interesting properties. But first, we have to describe what about Bose and Fermi statistics. For quantum systems, not all states are allowed, only ones that are either symmetric or antisymmetric, depending on whether they're bosons or fermions. And it's this requirement, which is the origin for Bose condensation, superfluidity, and the lambda transition that I'll talk about, or the transition to the superfluid state. What Feynman introduced was to use the permutation operator to project out the correct states. P here is something that interchanges the labels of the particles. And so you sum over all n factorial permutations. If you have some function f, any arbitrary function, and you relabel the particle coordinates every possible way, you will get a boson wave function, or you'll get 0, one of the two. If it has any boson component to it, this will project out the bosonic part of it. And so we can write the partition function as we can project out our expression for the density matrix by just adding the sum here, right? And so here is the probability of a given path. And so all this means is that the path closes on itself with a permutation of itself, as I'll show you in a second. And of course, we can't do, well, the approach that we're going to follow is not to sum over all n factorial permutations, because once n becomes a number like 100, there's n factorial is a large number, but we sample them, as I'll show you. So here is again my picture of 6 helium atoms, but here I've added a permutation. So basically, this atom one atom started at this position here, and it followed a path like this, and it ended up on the second atom's starting place. The second atom ended up on the third atom's starting place. And the third atom ended up back on the first atom, which, because of periodic boundary conditions, was the same as this atom, right? So this is like a wallpaper design of periodic boundary conditions. So, it's periodic in X and Y. These atoms, however, did not permute. So basically, the task of the path integral Monte Carlo for bosons is to sample all paths like this, or make a representative sample of them, plus all the different ways they could be connected up to each other. That is, that amongst the 6 atoms, there's 6 factorial ways they could be connected up, and you want to sample those too. Now, what you find when you do this, we did this back in the 80s, is that below a certain temperature, well, what happens in path integrals as the temperature gets lower? Well, the elastic band, the polymer gets bigger and bigger until at a certain point, one path overlaps with another path. Like these are almost touching right here. Then the entropy in the path integral allows them to interconnect like this, to become likely to interconnect. And you form a macroscopic exchange, and that's reflection of Bose condensation within path integral Monte Carlo. And here's examples of for helium comparing, this is in 3 dimensions. So here is the energy versus the temperature. And you see Bose condensation doesn't really have a big effect on the energy. If you just had Boltzmanns, that is not bosons, but particles that couldn't exchange, you would just follow a path like this dotted line. But you get this big reduction in energy, well, not big, only about 10% of the energy goes away. And essentially the system goes down into the ground state soon after the lambda transition. Here's the heat capacity, and you see it has a characteristic shape of the Greek letter lambda, and it goes to infinity here. And this is reflection of the phase transition. Why does this happen? Well, it's because in the quantum language, the system is releasing atoms are becoming delocalized, and they immediately go into the ground state that is below 1 Kelvin. In the path integral language, it's because you have these macroscopic exchanges which have a different kind of classical free energy. Now, the way to really see that it's Bose condensed is to look at superfluidity. Now, so that was the amazing property of liquid helium that was hard to understand, is how it can flow without viscosity, how it can be superfluid. Like electrons can become a superconductor, it's the analogous phenomena. And this was, Landau suggested in the 40s that you could measure the superfluidity by rotating the system and see if the system would flow. Now, if you, and Anna Kashvali did the experiment in 1946, he took a bunch of disks and he rotated them back and forth. And we can formulate this in terms of path integrals. So basically, if you take a cup of coffee, like I have here, and if you put it on a turntable and you rotate it, the coffee will rotate with the cup, right? And so you can measure the moment of inertia of the coffee by how much energy it takes to rotate the cup. And you see, you can measure the moment of inertia that way. Now, if it's superfluid helium, above the lambda transition, you rotate it, and you would find that all the helium is there, it rotates with the cup. But as you cool it down below the lambda transition, it will stop rotating. The helium will stop rotating, and so there'll be some missing mass. And so this is how you can define it. And it's actually a linear response or susceptibility in terms of statistical mechanics. And we can formulate this in terms of path integrals, by going into a rotating reference frame. And we find that the superfluid density is exactly given by the mean squared area of the path. So like here's a cartoon of those paths, and you see you can write, and there's little arrows here, you see, and the direction of the path in imaginary time. And so you can, so it's a signed area, namely if it goes clockwise from looking down on it, it's positive, and anti-clockwise, it's negative. Anyway, it's the mean squared area of the path, and that's the superfluid density. So the idea is if you just have little paths like that, the area is microscopic and there's no particular effect. That's classical response. But if you have a big exchange that takes up the whole volume of the system, then the area is proportional to the size of macroscopic quantity, and this would be macroscopic, and this would be on the order of 1. Now, to do this in simulations, we use periodic matter conditions. So you can take your system, which is a torus, and distort it, right? Like we can write a torus like this, right, mathematically. And we find that the area becomes the winding number when we do that. And so actually, and so this is the famous formula which we derived, this is something that Feynman sort of missed in his exploration in the 50s, that the superfluid density is basically the current in imaginary time path integrals. And it relates this topological property. In fact, I have a picture. This is the same picture here of the paths. And so this is a winding path, namely that if there's a current that goes through your system at imaginary time, and the superfluid density is proportional to that windingness. And so it relates the topological property of the paths to a dynamical response. And so a superfluid is a kind of a topological phase. And it shows that the imaginary time dynamics, how the paths are connected in imaginary time, is actually more important. And it's more important than something like the energy, which you don't see much effect of superfluidity in the energy. So here's a comparison to experiment. And that is these curves over here. This is the experimental, which is measured extremely accurately. Here's our calculations of 100 atoms. And this is the usual finite size rounding that you get in simulations. And so we agree more or less with the experiment, and now we could do much bigger systems. And actually in the 90s, Phillips and Zinger proposed doing calculations on helium droplets, and we came up with this curve, and we actually predicted that a small droplet of 64 atoms would become a superfluid, and this was verified experimentally about 10 years later by putting small markers in the helium droplets and molecules that you could observe spectroscopically. Okay, I would just close this section of the talk with talking about fermions. Now, suppose you want to do fermions. Well, you do the same kind of permutation operator, except now you have this uncomfortable -1 to the p to project out the anti-symmetry. Of course, there should be some spin labels, which I haven't put in here, but basically, for the moment, let's not worry about spin. This changes everything because Monte Carlo can't subtract very well. It can add very well, but not subtract. So this depends on the sign of the permutation. You can divide all permutations into even and odd ones, depending on whether you have to construct that permutation, whether you have an even number of two particle exchanges or an odd number, right? So these are 6 atoms, as I said before. These guys aren't permuting, so they don't count. But here you have an exchange of 3 atoms. That's actually an even exchange. So this would count with a plus sign. But if we had only 2 atoms on this exchange, it would be an odd exchange. And so basically, you could do this simulation perfectly fine, 6 atoms, there would be no problem, except you would carry along this thing as a weight. So this configuration would count as a positive weight, but the others would count as a negative one. But what you find is if you're looking to achieve an error of epsilon in some quantity, like the superfluid density or the energy or whatever, the computer time that you needed to get that accuracy would, well, it scales like 1/epsilon squared. That's just the Monte Carlo bad news, right? You have to run things longer to get a higher accuracy. But then there's this other factor which depends on the number of particles and on the temperature. And as the number of particles gets large or the temperature gets small, this is the free energy difference between Bose and fermion systems. Basically, it's the Fermi energy. This quantity blows up, right? So you can't do interesting fermion systems. I'd say these 6 particles are not too interesting, but once n gets to be 100, no matter what this is, if temperatures are down to the quantum degenerate regime, it's going to blow up, and your error bars, computer time to achieve a given error bar will blow up. And so actually Feynman pointed this out in his 65 book. It's very difficult to sum an alternating series of terms that are decreasing slowly in magnitude unless you have some other clue, right? And basically the path integrals, the imaginary path integrals, have not been that useful for Fermi systems. Now, there's one way around this, which we discovered, which was basically, it's called the fixed node method. Basically, you can restrict your paths to ones where your density matrix is positive. And this is an identity, actually, what's written here. The Fermion density matrix is given by the path integral, and this is the integral over all paths, but we restrict it to ones where the density matrix along the path is always positive. This kills this sign here, so you only have positive walks for things on the diagonal, that is for the partition function. However, the downside is that this density matrix appears both over here on the left-hand side and in the integrand, and nobody's figured out a way to do it self-consistently in many dimensions. And for one dimension, there would be no problem, but for many dimensions, it's difficult. And this is the Fermion sign problem, but it's still a useful method. I make an analogy to classical systems, like you're simulating a protein. Well, you don't know the potential energy of the protein, so you make a good guess, right, for the energy surface and a force field. And you still think you're learning something. So if you make a good guess for this density matrix, for this Fermion density matrix, then you can do the simulation. Okay. And I guess I'll skip over this hydrogen. I mean, Michele is going to talk about some results with hydrogen. We have done these path integrals things on hydrogen, which connected with electrons and protons, but the actual path integral Monte Carlo algorithm doesn't work well at very low temperatures. And so this is more useful for hot hydrogen, that is above, for temperatures above the degeneracy temperature. Maybe I should stop here for questions for the path integral, because I'm going to switch topics, talk about zero temperature methods now. Are there any questions in the chat, Sarah?
So we don't have questions in the chat at the moment. Maybe we can give it a second or two, or you can just keep going and then we take everything at the end.
Okay.
Just continue, David. Oh, sorry. No, we do have one question. Okay. So we have a question from Jeremy Richardson. He's asking, in what sense is the superfluid state protected?
Well, the superfluid state is protected in the sense that where you have this order parameter, which is the phase of the wave function, and it sort of sets up throughout your whole sample. And the only way you can change it is by putting in vortices, just like in a superconductor. You have to put in vortices, and they're not going to spontaneously arise in the middle of your sample. They have to come in either from the edges or from how you created the superfluid. Like when you cool down from a normal state to a superfluid state, there's this whole tangle of vortices inside. Okay, in that sense, they're protected. So there's an energy gap that is putting in a vortex, which costs energy, and which normally wouldn't happen. It's not going to happen thermally. It has to happen by how you make the superfluid.
Okay. Do we have more questions on this first part of David's talk?
Oh, are you asking me or no?
I was asking the audience, but I don't see anything. So why don't you
go
on and then we'll...
Oh, I have one more slide here.
Oh, okay.
On the path integral part, it's very interesting. We say that imaginary path integrals is isomorphic to a classical system. That is, you're mapping the quantum mini-body system into a classical system of these polymer-like objects, right? You have to be a little bit careful because there's a translation of words. It's like going from French to English. There's these false friends, right? And some words are not exactly the same. The free energy is exactly the same, but boson statistics corresponds to joining up the polymers like I described. Imaginary time velocity is like the bond vector, that is stretching of the spring. The kinetic energy, however, is the negative spring energy. And this is because you're in imaginary time. So IV squared is a negative number, right? And so the more it's stretched, the lower energy it is, which is opposite from classical. The momentum distribution is kind of interesting. Momentum is conjugate to position. So if you want to get the momentum distribution, you have to cut a polymer and let it open up. So I talked about ring polymers. Well, that's just for the potential energy, but for the kinetic energy, you want to cut one open and see how much it stretches out. And it'll be Bose condensed if it stretches throughout the whole system, right? So that's delocalization of two ends of a cut polymer. The superfluid state is like a microscopic polymer. The temperature is like a polymer length. And then we have a bunch of fermion words, like the Pauli principle is like restricted paths. A Fermi liquid are like winding paths in this fixed node approximation, or an insulator is like non-exchanging paths, right? So anyway, you have, and this allows us to think about these quantum systems in terms of our classical way of thinking, right? Okay. So now we're going to switch topics.
And David, I'm going to stop you just for a second because we have another question, and this one comes from Michele Casula, who would like to know how to sample permutations. What would you say is the most efficient permutation sampling method? That's, I guess, $1 million question.
Well, I can tell you what we did, and I can tell you what a lot of other people do nowadays. There are essentially two methods. I have some graphs on this, but I think I won't go into that. But we do well, maybe I should. This is the way we do it. Okay, so here we have 5 paths. Okay, we cut out a section like this. That is, this is imaginary time like that from 0 to beta. We cut out a section like this. We consider a section, and we decide to make a pair exchange. So here, the 5 paths are connected up in the identity permutation. They return to their starting place, but we. Sorry. Well, we cut out exchanges. Like that. And then we wire them in differently, right? And so now we have connected up a path where brown connects with green and green connects with brown. So this would be a pair exchange, right? We consider this as part of the metropolis. Now, the second method, which has gotten more popular because it scales better to larger n, is called the worm algorithm. And that's where you essentially cut one of the polymers and then you let this open end wind around your system until it meets up with the end later on. By that point, it may have joined itself to a lot of other polymers and it constructed a macroscopic exchange. Of course, in Metropolis, you have to consider reverse paths. And so that has to go back. You have to undo those paths too. Does that answer your question, Michele?
We're going to
Well,
assume that it does, and then if it doesn't, Michele can always pick it up again at the end of the talk. We have one more question, but in the interest of continuity, maybe, oh, Michele says yes, with an exclamation mark, so that's good. I would suggest, David, that maybe you can continue your talk, and then Pranay, we will ask you to pose the question at the end of the talk, so we don't break this one for too long. Thank you.
okay. Now we're going to switch over to zero temperature. And these are actually the more, what you may think more about quantum Monte Carlo. The first major quantum Monte Carlo calculation was in a graduate student, Bill McMillan at the University of Illinois, who did a variational Monte Carlo calculation for liquid helium. And he basically employed the Monte Carlo techniques that had just been developed 5 years earlier to liquid helium. And I'll describe that briefly. Basically, what is variational Monte Carlo? This is the variational principle here, right? You get an upper bound to the energy. Here, psi is a trial wave function. And this is the Rayleigh-Ritz principle. You want to calculate this. So basically, you do a random walk of psi squared, and you calculate this quantity, this ratio, by sampling psi squared, just like you would classically. And basically, you just calculate the energy in different ways. There are certain conditions on the wave function, like it has to be normalizable and continuous and have the right symmetry and so forth. In quantum chemistry, we'd use Hartree-Fock, but in Monte Carlo, we can use any wave function. And this has taken a new life in the last 5 years because of machine learning. People say, well, let's do some neural network to describe the wave function. But I'm going to describe kind of what the physics-based approach is. You try to understand what the wave function should look like. Now, in quantum Monte Carlo, what you want to calculate then, this in variational Monte Carlo, is the so-called local energy. And this is h psi over psi. That is, if you're going to sample psi squared, so you divide by psi squared here. So you end up with h psi over psi. And in Monte Carlo, it's the variance. So the energy, the upper bound to the energy is the average value of the local energy right here, right? But the variance is this thing squared, right? And if the local energy, if the wave function is good, the local energy is flat, and you have what's called a zero variance principle. And so this means that you can get highly accurate. As your wave function gets more and more accurate, your error bars get better. Now, what McMillan did is use what's called now a Jastrow wave function, although Jastrow was not the first person to come up with this wave function, but basically it's a pair product wave function, and you add this factor u. U is a variational function that is within the limits of the variational theorem. You're allowed to choose any u, and you can actually figure out based on these local energy arguments what good u functions are, right? You know, it has to be smoother than the potential, basically. Now, for fermions, you have to add an extra factor to keep them antisymmetric. But you know how to do that in Hartree-Fock. You have a determinant, right? A determinant of some single particle orbitals. And I wrote it down here for a fluid like liquid helium in terms of plane waves, filling up a plane wave. But if you're doing a solid or whatever, it's more block waves or whatever. And so you have, if you have n particles, n over 2 up spins, you have n over 2 orbitals. And your Slater-Jastrow wave function, well, if you're just doing its determinant, that's Hartree-Fock, and you know how to do that with analytically, if you like. But you can, if you add a Jastrow factor, you can express correlation directly, right? And there's special tricks on how to compute these determinants, and this becomes, instead of order n, it becomes sort of an n-cube kind of a method, right? Okay, but you can still do it. Now, you can actually do better wave functions than that. And here is an example. This is a Slater-Jastrow. Hartree-Fock, this is for the electron gas, that is just simply 1 over r particles. Hartree-Fock would be up here on the 5th floor, up here, and then you come down. This is the energy which you're trying to minimize, and this is the variance, that is the fluctuations in the energy. The variance should go to 0 if you have a perfect wave function. And so you can add three-body terms and what are called backflow terms and get better upper bounds. And you actually find that if you plot it energy versus variance, it typically lies on a straight line, particularly if you optimize things well, and you can kind of extrapolate to where the exact solution is, right? And so basically, as you add in these many-body terms. Now, the idea of machine learning is that maybe you can add in higher body terms, and using artificial intelligence kind of ideas, you can proceed to the exact solution. And I can't talk about that today, but that, it's a very promising approach that you can add complicated many-body terms that you wouldn't think of, and you could get down to lower energy. Now, the variational methods are powerful since you can use any trial function. The scaling is almost classical. You learn directly about what works in the wave function. However, the optimization is kind of time-consuming, and the energy is not necessarily sensitive to order parameters, for example, what you need to find in a phase transition. And it's difficult to find out how close you are to the right answer. So it's better to have a more automatic way. So I'm going to talk about projector Monte Carlo, but maybe nowadays people would talk about machine learning techniques as a kind of an automatic way here. Now, projector Monte Carlo was actually thought about by Fermi in the 1950s, and people tried it out then, but they didn't have either the methods or the computers back in the 50s. So the practical methods and applications were developed by Kalos in collaboration with Levesque and Verlet in '73. They did this calculation of 256 hard spheres using what we call projector Monte Carlo, and I'm going to describe a variant, which is called diffusion Monte Carlo. And it's very closely related to path integral Monte Carlo. Basically, you use the density matrix here as a way to project out the ground state. So the density matrix has this argument, which was beta before and now becomes T. It's the same parameter. And this, if you expand this operator in terms of exact eigenfunctions, you see that at long time, this projects out the ground state, because the long time means at low temperature. So essentially, you're going down to low temperature. The difference with path integrals is you're not timed to close the path. You're just using this operator to project out the ground state. Now, how do you do this on the computer? What's different? Well, let's consider this variable t as a continuous time. And so let's take the derivative of this equation, take the derivative with respect to t, and we end up with this dynamical equation, which we can regard as a master equation in statistical mechanics. Namely, this is the rate of change. If we regard psi as a probability distribution, the rate of change of probability is given by the right-hand side. And using Trotter's theorem, we see that there's two processes. Namely, there's the potential process and the kinetic process. This you recognize is just diffusion, and this is branching. This is like the decay of a radioactive nuclei is given by, this is the rate of change. And it not only can decay, but it can grow. But this requires the interpretation of the wave function as a probability density. So again, this is where the sign problem comes back in. Now, so this is the basic diffusion Monte Carlo algorithm. You construct an ensemble of what we call walkers. We have P ensembles. This is not a permutation. This is another P. And we go through the ensemble and we diffuse the particles according to a random number. And then we make a certain number of copies. And then we calculate observables at long time. And the ground state energy is the average value of the potential energy in this ensemble. But there's some problems they ran into in the 50s, namely the branching is uncontrolled. And so Kalos introduced the idea of importance sampling. And so basically the idea is you multiply the unknown function by a trial wave function that comes from variational Monte Carlo. And this changes the master equation. So we get this new master equation just by doing some algebra, right? And we have a diffusion term as before. We have a branching term, which is now the local energy. So now it's under control by your trial wave function. It's much smaller than before, and it's much more under control, especially the infinities. But as a compensation, we have this drift term that pushes the random walks away from places where the wave function is small. And so we can still apply Trotter's formula, and that's the diffusion Monte Carlo algorithm. Now, how can you do fermions? Well, to fermions, you can carry along, just like we did with permutations, the sign of the trial wave function, okay? And so depending on whether the wave function crossed the nodes of the trial wave function, you would have a plus sign or not. But you find, just like with path integrals, that the signal noise ratio goes to 0 exponentially in time. And so this is the Fermion problem, which I didn't say much about before. In a mathematical formulation, we would like to have an algorithm where the computer time would scale with a polynomial in the number of particles, right? With a reasonable exponent, right? And this algorithm here does not scale that way. As n goes to infinity, it goes exponentially in n, not as a polynomial. And if you could do this, this would say you would have solved the Fermion problem. And there are solved Fermion problems, I should say. Any one-dimensional problem, because basically exchange is equivalent to particles changing their order on a line. Bosons are solved, as I've showed you before. And some things like the half-filled Hubbard model or a harmonic oscillator could be solved because it can be related to a one-dimensional problem. The sign problem is very important. It's one of the biggest challenges in computational physics is and we know that there are some problems that can't be solved, but the question is whether they're interesting problems that you can solve, or maybe they're insolvable. Can we simulate 1 million hydrogen atoms with Monte Carlo without making an approximation? We can certainly do it with variational Monte Carlo, but that's an approximation. So that's the sign problem, which if there are younger scientists here, this is something you could work on, but it's not an easy problem. Now, the way we do it is what we call fixed node that I introduced you to before, is you impose the fixed node boundary condition, namely, psi t is our trial wave function. You say that the unknown function that you're trying to solve with has the same sign structure as your trial wave function, or it has the same phase if you're dealing with a complex wave function. You can prove that this gives you an upper bound if you use diffusion Monte Carlo. This is the so-called fixed node upper bound. And it would give you the exact energy if this were true, right? In fact, it gives you the lowest energy consistent with that constraint. And as you make the constraint better, you get closer to the answer. And so actually, this is the graph I showed you before. Remember, I had the Slater-Jastrow backflow, 3-body backflow. Now, if you use the fixed node, you end up, I can't calculate the variance very easily for that procedure, so I put it at 0 here. But if you take this wave function and you apply diffusion Monte Carlo with fixed node, you end up with a much lower energy. And if you use this backflow wave function, you end up with even lower energy, hopefully very close to the right answer here, right? So you gain a factor of 4. As I said, this is almost automatic. That is, once you program the wave function, the Slater-Jester wave function, or the backflow, then you pay a factor of 10 or whatever computer time, and you get this lower energy. Now, it is not the solution unless this is true here, and because it has a discontinuous gradient at the node. So there's one right at the nodal locations, you're not solving the Schrodinger equation. But the method scales well like variational Monte Carlo. It's just, a factor of 10 slower because your time step is slower. And you can generalize this procedure, as I said before, to finite temperature or a lattice or magnetic fields and so forth. So, okay, well, we're coming up to the hour now. So I'll try to wrap up here. The problems with the projector methods, well, it's like a super variational method. You don't necessarily break completely free from your trial wave function. So if your trial wave function is in the wrong phase, you'll stay in the wrong phase or whatever. The zero variance principle allows a very accurate calculation if your trial wave function is good. You have some difficulty with calculating properties other than the energy. There is something called Reptation Monte Carlo that solves this problem, introduces other problems, but I won't talk about that. I don't have time. But this last problem, it's a technical problem that can be solved with other techniques. So because the energy you get without a bias, but other properties are careful. In fact, Juha, I think, is going to talk about calculating forces, which have this problem also. Now, this is kind of one of my summaries of the projector methods. And so here is a log plot of your error bars and your computer time. Error bars is considered both the Monte Carlo error and the systematic error. So it's kind of a complicated diagram, but anyway, take a simple trial function, like a Jastrow trial function. You're computing along, this slope is determined by Monte Carlo. It's a 1/2, right? And but eventually you hit, in variational Monte Carlo, you hit the limits of your trial wave function. And you don't get any better. This is a systematic error of your trial function. You can switch to a better trial function and you'll follow a different line because of the zero variance principle. Both the intercept over here will be lower and the ultimate limit down here will be lower, but eventually you hit a lower limit. Now you can use fixed node. And so if you take your simple trial function, it's a little bit slower in the beginning, but eventually you get a better systematic error. But, you do have a systematic error. If you try to do an exact Fermion method, unfortunately, the slope is really slight, and it depends on the number of particles and how Fermion the system is. So it's hard to get down here. So the real key is to get better trial wave functions. And here is the golden area of good applications. That is, you want to not take too much computer time, and but your applications require a certain accuracy. So you want to be down in this region here, which is basically use better procedures and better trial functions. Okay. So here's my summary methods. I show you that methods that are used to classically can be used to solve these quantum problems, but they're only exact for thermodynamic properties of certain quantum systems because of the sign problem for fermion systems. Otherwise, they're variational. Now, I don't want to underemphasize this point. If you compare it to density functional theory, the density functional theory is not variational. So you can try a lot of different functionals, but you don't actually know when you're making improvement if you don't have any experimental or higher level results. With quantum Monte Carlo, you can see if things are getting better because you have a variational principle, and you can see if you lower the energy or not. You don't necessarily know if you have the exact solution always, but at least you have that you have a signpost that tells you you're going in the right direction. Now, I went through everything very fast. To see more details of everything, you can look in our book with Richard Martin and Lucia Reining. Came out a few years ago. Particularly chapters 22 and 25 go through everything I just talked about. So I'll stop there.
Thank you, David, for this great introduction to path integrals and quantum Monte Carlo methods. So I think we are ready to switch to the Q&A part of the session. Let me remind you, here we are going to authorize your mics, or rather to invite you to unmute your mics so that you can actually ask the question directly to David. And we're just going to go in order of appearance on the Q&A tab that I have here. So Pranay Patil asked a question pertaining to the first part of this lectures. So maybe we can ask him to unmute.
Hi. Yeah, so I had a sort of naive question about the sign problem. So if you can break up your ensemble into two pieces, one made up of all the positive weight paths and one of all the negative weight paths. And if you just sample the positive weight paths, can you tell anything physically relevant from that?
Well, any is a strong word, but no, you normally you can't really. I'm not sure exactly what you're thinking of, but
yeah, no, it was more of a yeah, I didn't have anything a particular example, but you mean to say that because the phase plays such a central role, if you were to just you would not be able to extract any even approximate value of any physical observable by just looking at the one of the sets.
Well, let's see. Well, first of all, for a wave function, if you integrate over the whole wave function, the positive part and the negative part are exactly equal, right? Because you just, by symmetry, anti-symmetry. So the correct observable would be 0, I guess. So it's essentially things go to 0 over 0, and you kind of, so I think the answer is not really. You can't really do it that way. I can't say that there's nothing that you can learn, but I don't think it's terribly useful. That's my...
Right. Yeah, because ideally you have this 0 by 0 form, and you want to do the limit carefully so that you extract some constant, right, from the 0 by 0 form.
You can still see my screen here, yes, here, right?
Right, yeah.
Okay, so here's a toy example. A particle in a box. It's hard to visualize things. Okay, so we have a rectangle here, and we assume that there's a potential that is symmetric about the center, which is this black dot right here. It's the center. And so we have this requirement on the box, right? We have inversion symmetry about that point. And the fermion state is the anti-symmetric state. If you were just solving this problem for a boson as symmetric, you would just let the particles wander around. That's fine. But we want to get this wave function, this anti-symmetric wave function. And a trial wave function would typically be simple. And this might be a trial wave function here, where the nodal surface is just this line here. And you would want to calculate something like the energy, which you would start a random walkout over here, and it would wander around, and it would have an initial sign and a final sign. That's what these sigmas are. And this is the 0 over 0 you just mentioned. And then you would calculate this local energy. I shouldn't have written it over here, but this the local energy, the final point is E of t. Okay, you want, or any observable, you would want to make a ratio like this. And the final state may have a different node than your trial state. It may look like this. I mean, this node, it has the node has to have the symmetry property, but this one does. It has inversion symmetry. And basically, because you have the initial state and the final state, after a while, because it's a Markov process, it's forgotten where it came from. And that's why you get 0 over 0. And that's why your signal to noise ratio goes to 0 anyway. Now, if you're just confining it to this region, you just don't get the right answer because you want to confine it to that region, but you don't know what that region is before you do the calculation. Okay. Now, if it's really just a two-dimensional box like this, you can invent a method. It would not be hard to invent a method that would self-consistently determine these nodes. But the problem is, how do you do this when you're in 1,000 dimensions? It's hard. Hard to do it because to self-consistently construct this node, you have to have a lot of walkers at every little point along the nodal surface. And you could do that in 2 dimensions because you can have billions of walkers. But if you're in a million dimension, it's like going out into outer space. The chance of running into anything is almost 0. You don't have enough information to constrain the nodes. Anyway, I'm not sure that answers your question, but.
Okay, no, I get a sense of why this it would completely miss the quantity, the relevant information, right?
I mean, you may get in a variation, you could do variational Monte Carlo that tells you, in that case, you can just sample over the positive region, but it's just that your region might not be correct.
Okay.
Right.
Maybe.
Okay. All right. Thank you.
Great. Maybe you can keep discussing this also in the gather session if you get a chance to interact. Then the next question comes from Paul Kent. Paul, you have the mic.
Thanks for the talk, David. So I have a sort of 2-part and quite general question. So you pointed out that machine learning is an attractive route to potentially finding high accuracy wave functions. And, given your perspective, I was wondering if you thought that this is the best way forward, because obviously in the last decade, there haven't been many new forms of wave function proposed using, fundamental physics and chemistry principles. So, did the community run out of ideas, or do you think there's unexplored opportunities there as well?
I guess the answer is yes. I mean, I follow the machine learning, and it's nice that there's some competition. Okay, it sort of encourages things, but I think actually there are very few attempts to use more complicated wave functions. There is the attempt of Marcus Holtzman and Sverre Moroni did this iterated backflow, and that actually got some very interesting results. But that showed its limitations too. I think the thing is to combine the 2 ideas together. If you just do machine learning without any physical constraints, I think you just sort of get lost into the world of high dimensional functions. You don't necessarily find it. We're trying to do something different than machine learning to recognize written language or whatever, which only requires something like 90% accuracy. We want really 100% accuracy when we do this. The And so I think somehow you want to guide the machine learning and the optimization. I mean, machine learning, that it's actually rather similar to it is an optimization method. And the idea is to guide that, to propose functionals which are physically correct. And another example was provided by Brian Clark and Sandra Cirillo, who have used the idea of sort of projector Monte Carlo to suggest new forms, new types of forms of wave functions for lattice models, and which can be applied to continuous models as well. Anyway, I think the machine learning is prompting people to consider new forms. I think what limited us in the past was the difficulty of coding more complicated forms. But with automatic differentiation and things like TensorFlow, it's possible that those techniques would actually be useful in proposing new forms. There's also the question maybe you're referring to about determinantal expansions, which have become quite popular, I guess, in quantum Monte Carlo, expanding things to determinant, but they don't necessarily scale well, but maybe they can be made to scale well techniques. So there's a possibility there of how do you consider determinantal expansions in a way that scale well. So anyway, another long answer.
But an interesting one, I think. Paul, do you have a comment?
I've been surprised at the relatively few number of attempts, at least in the published literature, to come up with new forms of wave function. So I think it's good to have this helpful, friendly competition. And also I agree totally with David that the newer tools such as automatic differentiation are going to make it much easier and quicker to try out different forms. So I'm hopeful and optimistic.
Okay. So I think that we have one more question from Michele Ceriotti. Michele?
Yeah. So thank you, David. It was very, very nice overview, very pedagogic. I still need to learn every time I hear about Monte Carlo, I learn something new. My question is also about machine learning, but from a more pragmatic perspective. And so I'm also noticing that there is relatively little activity in using quantum Monte Carlo energies and potentially also forces as targets for directly machine learning potential. And I'm wondering what are your thoughts if you think that the residual noise is something that would be detrimental. I tried and it actually seemed to work decently, but it was not very clear how accurate can you actually get with the presence of a residual noise.
Oh, okay. Well, we have a project of doing this for hydrogen. We haven't published anything. So actually, we know quite a bit about it for hydrogen. The initial problem was how to calculate the forces. I think without the forces, the energies alone, you don't have enough data to be terribly useful, although it's possible. Just the energies by themselves would be useful addition. But what we've done on hydrogen, this is work with, well, we gave a talk at the March meeting. You can see that talk last week, but we have computed something like 10,000 snapshots of dense hydrogen and the forces on 96 protons. And then we trained these using a hierarchical kind of a model where first we trained a DFT potential, sure, and then we trained the difference between DFT and QMC forces. And, it seems to work. And I think the accuracy is about a factor of 4 better than the error of the DFT. So, I mean, course, we don't know exactly what the error is, and it depends on the system a lot. But it seems like the QMC of running things for a few hours gives you, for each snapshot, gives you, you're able to distinguish between what we think the accurate forces and the DFT forces. And so this is giving you information that you can train on. Now, I should say that hydrogen is the easiest case for quantum Monte Carlo because of the pseudopotentials and because of the way things scale. So we haven't really gone much beyond hydrogen, although we would like to.
But in general, you don't think, because this is to me, it's an interesting question whether, because in many cases, the residual noise is something that you don't worry too much, because in a certain sense, it's largely uncorrelated. It really only hurts you when you're computing differences, right? And you can't use tricks to correlate the predictions. So because I mean, we did train a model on QMC target. I think it was the cheapo version, of course, not the very accurate version. But my impression was that the noise was not such a big problem, and so in the end, probably your accuracy is even more than what you could get from the residual from the variance that you still have. Do you get any indication in that sense?
No, I think you're probably right. I mean, that's certainly true that it's equivalent. I mean, I think what you're saying, we can express it in the following way. Suppose you have the question about whether to compute 10 snapshots to an error of epsilon, or 100 snapshots to an error of 10 epsilon. Or no, I didn't say that quite right, but I think you know what you mean. They're equivalent in the statistical sense.
Yeah,
it's better to get a broader range of snapshots. I mean, there are practical limitations, namely, you want to make sure that the systematic errors are the same and so forth. But in that sense, Monte Carlo is a big advantage. For example, in twist averaging and so forth, that the errors they don't bother you so much. And I think that's a useful thing to say, but you still have to get the error bars down to be on the order of the errors of the DFT forces, I think, so, in order to be useful. But that's my gut feeling. But we have achieved that for hydrogen, and there's no reason that we can't do it for other things too. The limitation so far, I think, has been the long-range character of the forces. I mean, that's kind of where we've hit the biggest error, is that the machine learning just doesn't treat the long-range forces very well.
Yeah. Thank you.
Okay. Thank you, everybody, for asking questions. Thank you again, David, for this talk. And I think we can now move to the next talk that is going to be presented by Juha Tihonen from Oak Ridge. So, Juha?
Yeah, hello, everybody. I can't seem to open my video yet.
Bogdan, Guy, help.
It's okay. I can use the meanwhile to, all right. Thank the organizer for giving this opportunity to talk what I think might be the most relevant audience on my humble scientific career to date. So I will be talking about the QMC forces. And I think David gave an excellent introduction to the QMC. And while I'm going to have a lot of information in a short period of time, I hope you in the audience can find a lot of connections to David's talk. So first, let me open with the motivation to, the concept of structural sensitivity of real materials. This is from a recent paper of germanium selenide monolayer, where they find that whether you use DFT or DMC to predict the structure of this material, especially the structural lattice parameters, you find a very different minimum for the energy surface, meaning that you predict a very different geometry. And not only do you get the lattice parameters wrong, you have a significant difference in the optical properties that you obtain from those geometries. So if there are any, or while there are probably many systems like this, we will want to have accurate theory such as DMC to provide the accurate DMC energy surface. And we want to also have means that are accurate and efficient to locate this DMC energy minimum. So my talk will, consider this question in two strategies. Firstly, I'm going to give kind of an introduction to QMC forces and some challenges that we found thereof. And then on the second part, I'm going to talk about this energy-based line search algorithm that we are in the process of proposing. So on the forces, as David told us, the QMC energy is quite established. It's variational, so we are sampling a trial wave function, and we can do different tricks to improve that. And since we are variational, we know exactly when we are improving and when not. So we have a powerful means of establishing accuracy. So if we want to improve the description in terms of a particular set of parameters, namely the atomic positions that I denote by lambda here, we can take the gradient of the energy and get an estimator for the QMC force. So a particularly popular estimator is this called zero variance, zero bias estimator, where we have a term for the bare force, which we call the Hellman-Feynman. Then we have a variance reduction term to that. And then to control any biases due to sampling a non-exact wave function, we need to have these zero bias terms. So it's all good. It mostly captures the force and is mostly consistent with the energy, say for some minor effects that we may not be able to address correctly. However, as you can see kind of on this busy slide already, it's growing a bit complicated, and even with these terms here, we face some troubles due to infinite variance problem and need to approximate this term, with in DMC simulation. So I'm not going to too much detail about this zoo of techniques here, but just to mention that we have been studying the QMC forces for 2 decades now, and on the bright side, we are kind of starting to see very interesting applications also using this estimator. For instance, people have done geometry optimization for a decade now. So the principle is that you can lower the energy by systematically minimizing the force. And when this is very established, you can extend the range of, or the size of the system, study some kind of physical properties such as bond length alternation, all that. And if it's established enough and efficient to evaluate, you can even do something like saturate the accuracy of the trial wave function with respect to the bond length properties using multi-determinants. And there are many other examples of this. I can't possibly be exhaustive here, but also there are other aspects to using forces, such as David mentioned, and that has been recently demonstrated by Michele and others, using QMC forces to train machine learning potentials and then run some other theory, such as ab initio molecular dynamics, to study, for instance, the phase diagram of high pressure hydrogen. This was published in Nature just last fall. Also, you can do phonon dispersion of solids, which was very recently done by this other group. And all in all, I hope this, for instance, demonstrates that you can do quite sizable applications of the forces already with QMC. However, it is my kind of grave duty here to report something from our recent work. Namely, we kind of found out about some challenges of the QMC forces when it comes to systems with high Z effective. And I'll just give an overview. I don't want to undermine the forces in this respect, but I guess the first step for us is to acknowledge whatever problems there are. So VMC altogether, when we target applications with high Z effective, may not be very accurate for transition metal systems, for instance. Even if it was, the consistency of the forces with the energy kind of suffers from different effects due to, let's say, the approximate DMC estimator, or using a gesture optimization procedure that is not fully variational, or using a plane wave representation of the wave function, which we often use in solid state, but which loses a lot of information of the gradients. Notably, I mean, all of these can be controlled to some extent, and it's just kind of extra sensitivity in the workflow, which doesn't seem to bother DMC PES so much. So if you can rely on DMC energies, you're free, mostly. The other problem is the infinite variance problem, especially with high Z effective, it intensifies. So I don't go into details of the problem. I'm just saying that there are good ways to control this problem as well. We are using this tail regression, where we kind of fit a tail to this heavy distribution of the force values so that we can get the error bars rigorously. And I'm pointing this out because it is due to this very estimator that we report some variance scaling properties. Namely, the variance, the statistical variance of the force seems to scale very rapidly with Z effective. Notably, it is more rapid than for energies. Of course, it is this might be dependent on the trial wave function and all that. So I guess the main point is that if you can afford something with energies, you may not afford it with forces. Anyway, since this is one of the main results, I want to go through an example of what it means in terms of the computational cost. And this is probably interesting to those involved in kind of force fields or other intense applications of the forces. So we have a model for the computational cost, where we have the number of atoms and the total intrinsic variance of the force, autocorrelation, computing time per sample. It's based on some assumptions, and we get a form such as this here, which enables us to kind of ask or flip around the question: to reach a constant accuracy of forces, what system size can we afford, and of what element? So taking, for instance, the 216 carbons, we get these two isocontour cost lines. And what it means is that if we go from the carbon to a heavier element, let's say 14 silicon, we can only afford at the same cost 16 of them. However, if we chose to use neon core potential, we could afford 570 of them, which is a sizable difference, and just saying maybe an interesting feature avenue for phonon dispersion. So with this data, we want to kind of emphasize that there are means to predict and justify different choices when it comes to kind of high-end applications of the forces in the future. On the other hand, if we want to target transition metals, we may want to exploit any further variance reductions that are possible. And actually, there is this thing called space warp. I'm overlooking the details here, but we also studied this with homonuclear dimers and found out that it indeed helps a lot. we get a reduction of the z-effective scaling compared to no space warp. So with the space warp in action, we can afford 30 to 90% larger systems all in all. On the other hand, it doesn't quite save you from the scaling altogether. So it's something to be mindful of when it comes to applying forces. Anyway, I wish I had something more kind of constructive to say about this, but I will now move on to this second part of my talk, which is kind of getting back to the structural optimization. And instead of using accurate energy gradients as a means of arriving at the minimum, we're proposing to use an approximate energy Hessian to kind of accelerate our way there. So as an overview of the method, we are kind of trying to reduce the complexity of the structural optimization problem as much as possible. Then we're using the surrogate theory, let's say DFT, to obtain many useful accelerations such as the Hessian and some error properties. And then we will sample sparse DMC-PES in line search iteration. And let's see how it looks. So by parametric model, I mean something where we can reduce the dimensionality of the phase space of the problem. So let's take chromium triiodide monolayer, where we have 8 atoms in a primitive cell, which we can actually, due to symmetry, reduce to these 3 parameters: the Dallais constant, a fractional x parameter, and fractional z parameter. So if we have this, we can do DFT to do a phonon calculation, or just a finite difference study to get a numerical Hessian for this structure with these parameters. So, and as we know, the Hessian expansion of the energy near the equilibrium looks like this. So we can, by using a number of energy evaluations, the squares with m squared, the scales with m squared, we could resolve the minimum. However, we can do better even. We can diagonalize the Hessian and get independent directions, a number m of them, which we can then independently minimize in order to arrive at the energy minimum, basically getting rid of this term here. So this gives us what we call conjugate directions, which in some proportion move around all the parameters that we have established. They have a characteristic potential energy curves. And as I said, if we minimize the energy along all of these curves independently or simultaneously, we kind of get to the answer quickly. To illustrate this on 2-parameter case of benzene, we see that if we use the original parameter directions, just like CC distance and HH distance in this molecule, we find out that starting from some displacement that is not favorable to these directions, we are facing a very slow oscillatory convergence to the minimum. However, if we use the Hessian conjugate directions that are characteristic to the PES, we kind of do it in a matter of 2 iterations. The first iteration is consumed by arriving at the very locality of the harmonic PES. Also in QMC, we are dealing with a finite statistical noise. So we want to ensure that we also, in the presence of noise, find this minimum with reasonable accuracy. And basically we expect to stay within a locality of the statistical fluctuation of around the minimum. And that actually brings me to an important part of this algorithm, which is the cost optimization and setting tolerances for this line search. Namely, with the DFT information, we know where the right answer is, so to speak, and we know the shape of the PES. So we may basically use statistical resampling to estimate the errors that come from doing a curve fit to find the minimum. And we can then kind of chart the shape of the grid and allowed noise to find the parameters for this particular line search, which maximizes our tolerance for noise while maintaining a tolerance of the resolution. So we can constrain the errors that we see. This is a bit more complicated when we have to balance it between all m parallel directions. There are means to do that. I won't go into details. So all in all, the main bottom line is that we can, with DFT information, control the error sources while minimizing the statistical cost. So this brings me to an overlook of the line search. We can use a structural model with few parameters. We can use it to obtain DFT Hessian starting geometry, and then we use the DFT to also cost optimize the line search settings. So then we can just plug it all in to this parallel workflow where we compute in any DMC workflow a set of energies, which can be done in parallel, and also we can do some cost savings in some parts of it even. And then in just a few iterations, we predict to have a DMC geometry of the equilibrium energy. And the nicest part of this is that all so far has been just basically an algorithm which can be used in any energy-based method where you struggle to get the forces like BMC, FGMC, stochastic configuration interaction, Simpson, you name it. So the question is whether it delivers with DMC, and indeed it seems to do. We made a couple of more examples with choroline and novoline, which is just flake-like molecules with aromatic rings. And due to symmetry, we can kind of reduce the structure here to 6 bond length parameters. In novoline, due to lower symmetry, we have to do 19. It doesn't really matter. We see that the directions or the changes in the parameters are strongly coupled most of the time, meaning that we really do need these conjugate directions in order to navigate the PS very efficiently. And again, it's like it's automated. I could give some physical insight to some of these bars here, but it's irrelevant in the end. The point is that if we plug this DFT information and some tolerances in DMC, we find that we indeed, starting from DFT geometry, we minimize the energy or minimize the parameter displacement from a predicted equilibrium very fast in just a matter of 2 iterations. And just to show, these examples contain a couple of dozen energy evaluations of DMC with error bars that depend really on the tolerances, but they are nothing heroic. So it's quite cheap, it can be cost optimized, and it's nice. So this brings me to the summary. We probably want to do structural optimization of certain sensitive real life applications, and we want to do it with QMC to maintain good accuracy. However, while the QMC forces are really showing great promise on high impact applications with a low Z effective regime, they seem to face challenges in systems with high Z effective. So while we are working on those, we want to do this, we propose to do this energy-based line search that uses DFT information for acceleration to optimize the DMC energy. Also, we have already demonstrated this method with a bunch of materials and molecules with up to 19 parameters, and it can be actually generalized to any energy-based method. All right, so with that, I'd like to thank you for listening, and also especially my co-authors, Ray, for making sizable contributions to the force estimators, and Jaron for figuring out the theory of the line search method, also funding and institutional support from other sources. Thanks.
Thank you, Juha. The talk is now open for questions. While we wait to see if we have any from our audience, maybe I can ask one. Have you looked into the effects of the accuracy of the initial DFT information on your final result? I mean, can you get stuck in a wrong minimum because you start from information that is not accurate enough, for example?
Well, we have not really done that, and we expect in many of these cases that there wouldn't be very close by local minima of the energy. Of course, that's possible, and actually, on the other hand, we do have means to assess that. Namely, when we explore the PES for establishing the error bars and all, we actually explicitly compute the energy surfaces. And so if there's any strange shapes, dual well structures or something like that, we'll see it immediately from looking those curves. And actually, if you try to expand the search grid too much, you will finally have trouble with the SCF, or physically you will encounter different shapes of the PES. And typically, though, the DFT starting position is quite close to the DMC, or close enough so that we shouldn't be running into that problem.
Okay, thank you. So I don't see questions from the audience, but I would like to remind everybody that Juha's talk is also available as a poster in the Gather poster session that will follow this part of our interactions. Wait, okay, I see that Saverio Moroni has raised his hand, so maybe we can invite him to contribute and ask the question. Okay, let's see if, Saverio, I think we have invited you to unmute yourself if you want to ask your question.
Okay, thank you. Can you hear me?
Yes.
Okay, you mentioned the problem of infinite variance in the force, and you cope with this problem using this this Taylor regression estimator, right? And you find a certain scaling with the number of the number of electrons in the atom, and it's very bad, I would say, much worse than the energy. But what about if you use other regularizations, such as the guided function that you mentioned, or the Patak-Wagner regularization? These actually make the variance finite. So I would expect that both the value of the variance and perhaps even the scaling will be better.
Yeah, that's an excellent question. It would be something I was wondering myself as well. What we have found so far is that with the systems that barely show the heavy tails, we don't get much difference between the tail regression estimator and the force value using standard means of statistical analysis. So this means that in some systems, the heavy tails are practically formal. It's possible that we get spikes, but they are not very frequent. So in that sense, our results should match whatever you get by using the guiding functions. I'm not sure if that holds with very heavy elements where we do have much more presence of the nodes. So we haven't really comprehensively run the guiding functions ourselves in these regimes. But my personal expectations would be that it doesn't make a sizable reduction of the statistical or the variance, whether we use guiding functions or the tail regression. So most of the variance really comes from other parts of the sampling procedure than the very nodal divergences. I could be wrong.
Okay, thank you.
One more question from Kozuke Nakano.
Yes, can you hear me clearly?
Very well, thank you.
Okay, thank you for citing our recent work. You said in this presentation, you write VMC may not be accurate enough to study high Z effective transition metal compound, right? So does it mean a force obtained from the potential energy surface is not consistent with the VMC force?
Well, okay, that's a very dangerous statement that I made actually, because the whole question of accuracy has so many parameters, like the trial wave function that you use, and well, I guess mainly that, really. But we did some studies with single determinant two-body Jastrow wave functions, which is not very advanced for VMC in these systems, and found that the accuracy is not really quite good enough in dimers. It doesn't mean that with using better trial wave functions you couldn't overcome these effects, but I guess you could consider it as a further complication. You can just, in the same way that you can just use this simple trial wave function with VMC, you can't barge in with VMC and expect as accurate results, which was actually made nicely clear by David in his talk.
Okay, thank you very much.
So I don't mean to doom the use of VMC in those systems. It just it requires some extra care.
I see. Oh, but so let me ask another question. Here, high Z effective. Okay, from so what atomic number do you intend? Let's see, for example, for iron, for titanium, or in my case, carbon. In the carbon case, VMC force works, but I'm not sure. I have not tested the larger atomic number atoms.
Yeah.
So,
I mean, well, Z effective with pseudopotential for carbon would be 4, and
yes,
we started them up to 20, which is zinc.
Oh, so, zinc. Okay. So, for example, for carbon case, you also got inconsistent forces here.
Yes. Yeah, that's because we didn't use the appropriate orbital rotations with the Jastrow optimization. So it depends where you draw the line of accuracy for the self-consistency of the forces with the energy. Like, there will be minor effects, or at least it's minor if you consider it's minor.
Thank you very much. Okay, I see. Thank you very much.
Okay, good. Thank you, Juha, again for this talk. I think we are ready to move to the last talk of this webinar session. So, Michele Ruggeri, QMC determination of the principal Hugoniot of deuterium. You have the floor.
Can you hear me now?
Yes.
Okay. So hello everyone, and thank you for being here today. I'm Michele Ruggeri. I work as a postdoc at Maison de la Simulation at the CEA-Saclay near Paris. And today I'm going to be talking about my work, of my co-workers in quantum Monte Carlo simulation to determine the principal Hugoniot of deuterium. I'm going to start this presentation giving some context about what is the principal Hugoniot and what is the motivation behind our work. So one of the ways to investigate the properties of materials in extreme condition, and well, in our specific case, hydrogen and deuterium, is given by Shopper experiment, which are performed in facilities such as the Z machine in the Sandia National Lab in the US. In this kind of experiment, we take a sample of our physical system, we prepare it in an initial state, and then we subject it to a short duration and intensity force. Then we let the system relax, and we measure its properties. After the shock, with the relaxation, the properties of the system will be determined by the Ugonio-Rankin relation. If initially the system at rest has energy, specific volume, and pressure given by E0, B0, and P0 here, after shock and relaxation, the final properties of the system must satisfy this relation here, which is itself a consequence of a conservation law in fluid dynamics. So what does it mean? It means that after we do the experiment, given the initial state, we measure the pressure and the density of the system after relaxation, and we obtain this kind of plot. This is taken by an experimental work by Knudsen, in which the several data obtained with different experimental setup is compared. Of course, we work in theory, so we may wonder if it is possible to describe this principal Ugonio using ab initio electronic structure methods. In general, the two techniques which used to describe this kind of experiment are density functional theory calculation and quantum Monte Carlo simulations. Usually, DFT results are in pretty good agreement with experimental data, agreement which is also pretty independent on exchange and correlation functional. Here it can be seen, hopefully, seeing that this round point and the triangle correspond to DFT calculation, which are pretty on spot with experimental data. On the other hand, unfortunately, quantum Monte Carlo simulation are not in such a good agreement. And in particular, pretty systematically show a larger compressibility than what is measured. So our motivation here was to see if we can obtain a better accuracy using a quantum Monte Carlo method using a new simulation protocol based on coupled electron ion Monte Carlo. So I will discuss now a bit the coupled electron ion Monte Carlo method that we use. So coupled electron ion is a quantum Monte Carlo method which is used to sample both the distribution of the ions seen as a finite temperature system and to simulate the electrons. In particular, the ionic system is seen as a finite temperature system, which can be classical, so formed by classical point-like particles, or a quantum system, which is described by the Path integral polymers described by David before. And the probability distribution of the ionic configuration will be given by the Boltzmann weight, e to the minus beta e, where e is the Born-Oppenheimer energy. This Born-Oppenheimer energy, in turn, is computed by simulating the electron using ground state quantum Monte Carlo methods, such as the Variational Monte Carlo or the Repetition Monte Carlo using a fixed approximation. And the Repetition Monte Carlo here is just like the Diffusion Monte Carlo discussed earlier, a projector method based on imaginary time evolution. So the idea is that again we move these ionic particles in an energy landscape which is given by the Born-Oppenheimer energy. So in general, each time we try to move the ions, we need to know the difference in the Born-Oppenheimer energy before and after the move. In principle, we should be doing quantum Monte Carlo simulation for each attempted move, but since this is not very efficient or practical, correlated sampling is usually used. The problem unique to this method is the presence of the statistical noise in the difference of the Born-Oppenheimer energy, which, since it is used in the metropolis sampling to in the Markov chain that we use to sample distribution, can give a bias to our estimate. In order to deal with this problem, the penalty method is used, which is essentially a suppression on the acceptance probability of each move which increase as the variance of the Bohr-Oppenheimer energy increases. Moreover, other measures are used to improve the efficiencies of this method, such as the rejection of ionic move using effective potential, which is to discard proposed move which lead to grossly unphysical or very unlikely configuration, which is used using classical effective potentials, which are system dependent. And also, even if we may be doing BMC or Partition Monte Carlo calculation at each step, optimization is not repeated in the simulation. There is only one optimization step, which is doing once at the beginning of the simulation, and then the optimized parameters are used during the whole simulation. A related method that I want to mention, and that we also used, is the DFT Bohr-Oppenheimer Monte Carlo method, which is very similar to coupled electron Monte Carlo, in the sense that it's a way to sample the ionic configuration in a Bohr-Oppenheimer surface. But in this case, the Bohr-Oppenheimer surface is not computed with quantum Monte Carlo, but with DFT simulations. So to compute the Ugonio, the simulation protocol that we use is as follows. We simulated different systems. So for the reference state at low temperature, at temperature of 22 Kelvin at low density, plus a set of high temperature, high density system. For each of these systems, we generated about 100 configuration, which will be representative of the liquid state. 12 these configurations, which are statistically independent and representative, we took a snapshot from path integral simulation, which for the reference state were taken from path integral Monte Carlo simulation, obtained using effective potentials, and specifically the Kolos-Volyniewicz and Silvera-Goldman potential. While for the high temperature system, we use coupled electron ion. Then for each configuration, we separately optimize the triwave function. Then we use the variational Monte Carlo, adaptation Monte Carlo, to compute the energy and the system. Once we have the energy and the pressure for each configuration, we average them to obtain the average property of these of all temperature and density sets. Then using linear interpolation, we obtain the Ugonio density and the corresponding pressure. Now, a few couple of technical details. Our triwave function here we're of the Jastrow-Slater form using backflow transformation. In the Jastrow factors, we included 1, 2, and 3 body terms. And the single particle orbitals used in this data determinant were computed with DFT using PBE orbitals and the quantum espresso software. The backflow transformation that we used were analytical backflow transformation, which are detailed in this paper. Moreover, since we simulated a system made only a few tenths of deuterium atoms, we had to deal with a size effect. And to reduce the impact of this size effect, we use twist averaging using a 4x4 grid in K-space, and including 1 and 2 body size correction. An important thing that I need to point out is that we need to have accurate estimates for the reference state, because even a small deviation in the evaluation of the energy of the ground state may lead to significant variation of the position of the density of the Ugonio. Moreover, we computed the reference state, the energy of the reference state with variational DFT and computation Monte Carlo. And in the computation of the Ugonio, in each data set, we used the reference state computed with the same method to be more consistent and to have helpful error cancellations. Now I will move on and discuss a bit the result. Here, I'm showing the Gonio function as a function of the density for 3 different temperatures: 2000 Kelvin, 4000 Kelvin, and 8000 Kelvin. The results are shown for Variational Monte Carlo, the purple line, Computational Monte Carlo, the green data set, and then for the Born-Oppenheimer Monte Carlo, which is the blue line. The shaded region here refers to the statistical uncertainties of the fit. Something that we can see observing this plot is that the Variational Monte Carlo data show Gonio density, which is systematically lower than the one obtained with Computational Monte Carlo. And also we see that especially the lowest temperature, the scale on the Gonio axis is much smaller than the other. And so some uncertainties, for example, on the reference state due to other effects, may lead to much larger variation on the position of the Gonio. There are other effects that I'd like to discuss before having a look to a comparison with our data with experiment, which are electronic thermal effect and nuclear quantum effect for this system. So I started with discussing electronic thermal effect. Here we are always working at temperatures which are of the order of several thousand of Kelvin. But we always use to deal with our electrons a ground state method, variational adaptation Monte Carlo. And a priori is not trivial saying that we can completely discard electronic thermal effect. To understand how much this electronic effect may affect our result, we started having a look at the density functional theory results. Here we compare the computation of the Gonio, the threshold as functional temperature, and the Gonio curve obtained with finite temperature DFT, which is the data set. No, sorry, the blue data set, and the ground state van der Waals DF1 DFT. Here we can see that the results are essentially perfectly overlapping up to a temperature to 10,000 Kelvin. Which is to say that in the temperature range in which we are working, ground state DFT seems to be very accurate. The problem is, how can we say the same for our Monte Carlo results? To do that, we computed excitation energy with variational Monte Carlo and DFT, and we compare those. So in order to compute excitation energy with variational Monte Carlo, we computed energy using BMC, included in the zeta determinant in our tri-wave function, single and double particle excitation. Then we took this excitation energy, so we took the energy with excited state and subtract the ground state energy, and compare those with the constant spectrum from DFT. What we can see here from this plot is that even if the absolute value of the energies from the BMC and DFT are different, the energy with respect to ground state is really similar. And since all the thermodynamical properties of the system will depend on the Boltzmann weight, so in particular on e to the minus beta times the excitation energy, we can expect that the DFT and quantum Monte Carlo behavior in this case will be pretty similar. And so we should not expect a thermal effect in the temperature range that we are simulating. Another effect that may be relevant is given by nuclear quantum effects. Yeah, in general, in hydrogen and deuterium, nuclear quantum effects are very important, and they can be seen, could be seen even at a high temperature. In order to have an estimate of the extent of the use of quantum nuclei in our simulation, where we compare the energy, pressure, and the Ugonio obtained with one of the Oppenheimer Monte Carlo using classical and quantum nuclei. You see that the difference in energy, pressure, and especially in pressure, is not that large. But in the Ugonio, the inclusion of quantum effect leads to a displacement of the Ugonio of about 1 milliards. That, if we go back here, can be definitely relevant in this energy scale. Which, but on the other hand, is not completely negligible for the higher temperature data sets. So finally, now I want to discuss my results and compare them with the experimental data obtained by Knudsen and co-workers, and also with the previous quantum Monte Carlo studies with Tubman and Clay. So here in this plot, our data is teal for the Oppenheimer Monte Carlo result, and red and blue for the variation and adaptation Monte Carlo, respectively. The full symbols refer to a result with classical nuclei, while the open ones refer to results in which nuclear quantum effects are included. Here we see that at the lower temperatures, our results are pretty good agreement with the experiment, especially at temperature of 2000 Kelvin. Perhaps a bit surprisingly, the variation Monte Carlo result seems to be even in better agreement with the, in principle, more accurate adaptation Monte Carlo result. Going on, we see that going on increasing the temperature, we see that even at 4000 Kelvin, our results are in much better agreement than the one obtained by Tubman in 2015, and the agreement is comparable with the one obtained by Clay, even if our results are not really in agreement one another. However, at the highest temperature, here we see that even if the result of our simulation are closer to the experimental data, we are not in especially good agreement. Yeah, and so yeah, here the temperature there seems to be still some problem. One possible reason could be that at the two lowest temperature, our system is a molecular liquid, which can be pretty well described in the quantum Monte Carlo simulation. While here there is a dissociation which is still ongoing. Our structural analysis predicted about molecular fraction about 10–15%, which could be harder to describe with quantum Monte Carlo. So that should be more or less it. Summing up, I've shown this procedure for the study of liquid deuterium, in which we generated nuclear configuration from a partition method, coupled electron or partition ground state. And then we used the VMC and rotation Monte Carlo to simulate the electrons. I've also shown how it is possible to estimate the effect on thermal, electronic thermal effect and nuclear quantum effect in quantum Monte Carlo simulation. And we did manage to improve the quantum Monte Carlo description of GON, especially at temperature equal or lower than 4000 Kelvin. Again, where experiment is, I would say, good, while at the highest temperature, there is still some issue to be addressed, which is probably linked to the ongoing dissociation of the system. So thank you for your attention. I want to finish this talk by a shout out to my co-workers, Carlo, Marcus, and David. And this work was made possible by funding from the European Union project, ICAM and ECO2. So thank you for your attention.
Thank you, Michele.
Any question, Anita?
Thank you, Michele, for this nice talk. Yes, so the talk is now open for questions. While we wait to see if there is anyone from the audience, I have a very general question, and I mean, you or maybe one of the other experts, but if we had to include excited electronic states, what avenues are available to us? And I guess it would be a much harder problem, but.
Well, it is possible to, it is in principle possible to do a fast integral Monte Carlo simulation for fermions to include thermal effect for the electrons too. But this kind of simulation is pretty hard to do, and also problem linked to, well, there is a very bad sign problem, of course. And so yeah, that's the main obstacles. I mean, also, here, what we did was include just one excitation, well, single or double excitation at the time in our simulations, because especially in condensed matter system, if we wanted to include a lot of excitation, would have a very large and huge number of excitation to be taken into account, which are very close to the Fermi surface. So even if at relatively low temperature, it's really a large number of excitation to be taken into account.
Okay, thank you. So as in the case of Juha, also Michele's talk is available also as a poster in the Gather session. So if anybody from the audience is interested in having a one-on-one discussion with Michele, that's an opportunity to do that. Since I do not see raised hands or Q&As, I think we can move. Oh, David separately has raised his hand. So David, do you have a comment?
Well, no, on what you just said. What Michele is showing here is at low temperatures, you can actually just do the excitations. But as you get to higher temperatures, then you can switch over to path integral Monte Carlo, which would consider, you're not considering individual excitations, but you're considering the whole thermal density matrix. You don't have to single out the excitations. And it seems like there's the methods sort of overlap. So you might be able to cover all the temperatures that way.
Okay, thank you, David. We have a question from Michele Casula. Michele?
Yes, so thanks, Michele, for your nice presentation. I have a question about your last plot, where you basically, yes, you put together all your results. So I'm kind of impressed by the quality of DFT Born-Oppenheimer Monte Carlo. Is Born-Oppenheimer Monte Carlo, right?
Yeah.
What you BOMC, right?
Yeah.
So I mean, you're wondering why you get this disagreement at a large at higher temperature, and so could you learn something from the results from DFT? So first of all, which is the DFT you're talking about here? Because I mean, I guess you get different results from different functionals. Yeah. So it's important, I think, to clarify what is the DFT functional you're using. Yeah, I mean, you show here. Because I mean, the quality, I mean, the agreement with the experiment is quite impressive. I mean, in that case, so maybe we can learn something from DFT already before addressing the question about quantum Monte Carlo.
Well, here, the DFT user is Van der Waals DF1 and DFT. And well, yeah, in general, DFT tend to be very accurate in describing the experimental result of Ugonio. And also this accuracy is pretty independent from the function which is used. I don't know if it was visible here. There are a lot of DFT data sets here which are essentially in very good agreement with the experiment. So for example, it's not to say that if we were to use orbitals obtained with Van der Waals DF1, I would expect our result to dramatically improve. Yeah,
So
not sure
like
what's
that
going to happen.
Dissociation you basically invoke to sort of understand the slight disagreement you have at higher temperature can be seen from DFT results. If the you're trying to understand what is the disagreement you have between the experimental points and your findings. So you mentioned about dissociation as a possible source of disagreement.
Mm-hmm.
Is it something can be seen also from in DFT or not?
Yeah, usually the DFT Bono Oppenheimer Monte Carlo is pretty accurate and very much the result on the structural analysis, for example, between the G of R and or other estimators are pretty much in agreement with quantum Monte Carlo. So it's not the structure computed with the different method is very much different. Or well, different at all. So,
okay, thank you.
Okay, we have one more question from Cody Melton.
Yeah, so this is more just a comment based on the previous question. But if I'm not mistaken, so the paper by Ray Clay that you're citing, the reason that DFT is doing so well is that it is relying more on error cancellation. I think they showed that whenever you move to the mini-body methods, that it's more likely, or it's possible that you end up getting error additions instead of error cancellations, whereas in the DFT, error cancellation ends up happening more often. And so the Hugonio looks better. But whenever you move to the mini-body methods, it becomes more possible to have error addition just due to the functional form of the Hugonio.
oh yeah, definitely. There is this thing, yeah, that usually error cancellation helps quite a lot, the DFT. So maybe an explanation of why such different functions give all these wonderful results, the same result. Yeah, with DFT is not that easy usually. Yeah, thanks for the comment.
Okay, so if we don't have any more comments or questions, maybe we can move towards the end of this part of the session by thanking again all our speakers. And before parting, let me just remind you of our next session of the Mixed Gen series organized by SICA. So this is going to take place on April 8th, same time, same place. And the topic is going to be data-driven science. Our experienced speaker is Claudia Draxler from the Humboldt University in Berlin. The title of her talk is From Data to Knowledge. If you are curious about this next talk or anything that's happening in the series, you can find the information on the SICAM website, www.sicam.org/mixedgen. And if you scroll all the way down to the end of that page, you will also see that there is a little window where you can register for the mailing list that we use to disseminate information about this event and other activities that we promote at SICAM. Then you can also follow us on Twitter, SICAM events, and you will get information about all our activities and also updates on the status of our flagship program, which is of course quite affected by the current COVID pandemic, but some workshops and schools are moving online, others are being postponed. So, keep an eye on the website and on the Twitter, and you will be up to date with information from us. With that, I would like to thank you all for participating to this session of the Mixed Gen SICAM series, and we're looking forward to seeing you soon. If you are registered for the second part of this session, which is the poster session, do join us on Gather Town. I think we can take a 10 minutes break to have some coffee or tea and recover from the fatigue of the Zoom gatherings, and then meet again in this more informal environment. Thank you very much.